who is going to tell us about the toric case of the Thomas-Yau conjecture.
Okay, so thanks to all the organizers for this nice opportunity to present this work. Yeah, so it's about something called Thomas-Yau conjecture, or conjectures in the plural, and so let's see what this is about. So the context is that of Calabi-Yau geometry. So we have a complex manifold. It could be non-compact. Actually, it will be non-compact in most of our applications. And at the same time, it's a scalar. So little omega denotes a scalar form on X. And there is also a holomorphic volume form, which is in the fixed complex structure. So this such a triple is sometimes called almost Calabi-Yau, which means that we do not necessarily enforce that we have the complex motion pair equation holding on X. And this equation here for which is relating the holomorphic volume form to the metric form in the strongest possible way, and which implies Ricci flatness of the metric underlying our scalar form. So if we do without this condition, some people call this almost Calabi-Yau geometry. So that's roughly the kind of geometry that we're going to work on. But it will be much more special than that, as you will see in a few minutes. So, so let's suppose now we have some embedded submanifold of real dimension half the dimension of X. So it's a real n dimension inside the X, which is complex n dimensional. And so we have a symplectic form. So the scalar form is in particular symplectic. So it makes sense to speak of Lagrangians inside X. And among all Lagrangians, we want to single out some particular ones which which solve a partial differential equation, which is very much studied, and it is called the special Lagrangian equation. So the condition is that if we restrict the holomorphic volume form which we have on X to this embedded submanifold, then we get a form which has constant phase. And this phase we call X per I theta hat. So up to, so in other words, if we scale by the inverse of this phase, we get something which is a real form when restricted to the submanifold. And so this is a classical topic of study in different areas. So, for example, one reason people are interested is that it relates to the calculus of variations to minimal submanifolds. So if the precise statement is that if X is actually Calabi-Yau in the strong sense, so so omega is Ricci flat, and if the Lagrangian is compact, then if it's a special Lagrangian, then it minimizes the area in its cohomology class. And so in particular, it's a minimal submanifold, but much more than that, it actually minimizes the volume. The reason being these inequalities, which are altogether called the calibration inequality, I think, sometimes. And so this is something that holds in general for Lagrangians, and you see that it's so that these equalities are achieved precisely when L is a special Lagrangian. So you get this minimization property for area. And related to that, there's also a strong relation to the mean curvature flow. So it's known that in the strong Calabi-Yau case, the mean curvature flow of submanifolds preserves the Lagrangian condition. So and that special Lagrangians are then stationary points for this flow. So the rough picture that you would expect is that if you start from a Lagrangian and try to minimize its area by flowing through the mean curvature flow, then perhaps in the limit, if you're lucky, you will get a special Lagrangian, which is a strong minimizer of the area. So this is one reason why at least one community is interested in such objects coming from geometric analysis and the calculus of variations somehow. So another main source of interest in such submanifolds is from physics, or something that some looks like physics. I'm far from a physicist myself, but I think the right words to say are that if we are in the compact Calabi-Yau case, then we can, or physicists can imagine, they can formulate a theory which is called the type 2A string theory compactified on X. And A somehow is a reminder that we are dealing with the Lagrangians. So field configurations in this theory have to do with the Lagrangian submanifolds inside X. Somehow there are so fields configurations are related to Lagrangians, and the special Lagrangians are some of these field configurations that somehow saturate an energy bound. So physicists call such a bound relation between the energy and the central charge, and these special Lagrangians are precisely these configurations which achieve this this bound, which is called the BPS, or Mogomani-Prasad-Sommerfeld bound. And so they are particularly important field configurations in your theory. And I think so this BPS bound for this type 2A theory is in fact more or less the same as this calibration inequality. And so BPS states are those which saturate this calibration inequality. And but so, okay, so what is highly non-trivial somehow from this physics viewpoint is that there is an alternative but equivalent formulation for the same theory, which is type 2B, formulated not on the Calabi-Yau X, but on some other Calabi-Yau manifold, which is called the mirror to X. And physicists somehow expect, but actually I think for them it's more or less a classical fact, so it's a fact of nature for this type of physicists, that the two theories are in fact equivalent, so it's old physics for them. And so more or less, so the physical observables must be the same in type 2A and 2B. And 2B is related not to special Lagrangians or Lagrangians in general, but to holomorphic vector bundles. So somehow you would expect to see some highly non-trivial correspondence between Lagrangians and holomorphic vector bundles. And that's precisely this mirror symmetry theory, which is by now a purely mathematical subject of study, of course. Okay, so this was so the motivation that led to the original conjectures by Richard Thomas and later Thomas-Yau. So the general question is, can we basically, when can we solve this special Lagrangian equation? Or more precisely, in the original papers, the question was formulated using the Hamiltonian isotopic class of a given Lagrangian. So we ask ourselves if we can so deform a given Lagrangian within its Hamiltonian isotopic class on Calabi-Yau to get a special Lagrangian, to a solution to this geometric PDE. And Richard's original idea was that this solvability somehow should be a stability condition for the given isotopic class, which is somehow analog to slope stability or Mumford stability for holomorphic vector bundles. And essentially his reason was that you can set up this dictionary between holomorphic vector bundles and Lagrangian subvarieties coming from this type 2A, 2B correspondence, or more mathematically mirror symmetry, which at the time was really not known in any case and was highly conjectural. And yeah, so this was his expectation, and in the original paper, and then in the paper with Yau, they had precise ways of formulating this kind of expectation, but we're not going to review them because some of it seems that they've been superseded by more recent developments, although some of them remain very, very important as a source of all this story. So this happened around 23 years ago or so. So more recently, there have been different interpretations of this conjecture, and we will see some of these things. So firstly, there's a memoir by Dominic Joyce with a very long title, but the initial part is the conjectures on Bridgeland stability for Fukaya categories. And we will see an example of one of these conjectures soon. They are perhaps the most precise way of formulating this idea that the existence of special Lagrangians has to do with some stability condition which looks algebra geometric somehow in nature. And then there's another memoir, it's a rather amazing book, really, by Yang Li. It's called the Thomas-Yau conjecture and holomorphic curves from a few years ago, which has a different focus. So it's not so much focused on Bridgeland stability and the mean curvature flow, but rather some more direct variational methods to attack these kind of conjectures. And yeah, it's a great source of ideas and results, really. And one point is that it really emphasizes the need to work beyond the Calabi-Yau case in the almost Calabi-Yau. So the fact that to achieve some kind of genericity, you need to be able to perturb away from the Calabi-Yau condition, so relax this Ricci flatness. This is so important for us because we are going to work in a class of examples, which is certainly not Calabi-Yau in the strict sense. But in both cases, so for both of these monographs, one common key point is that they supersede this idea of working in a fixed Hamiltonian isotopic class, and they emphasize the need to work with a suitable version of the Fukaya category. So a category whose objects are Lagrangian branes, and that some categorical information should be really crucial to formulating and actually, hopefully, proving these kind of conjectures. So this is something that we will see in our simple examples. So I would like to give you some feeling for starting with Yang Li's result, for example. So the setup he considers is a fine, essentially. So it's a Calabi-Yau, which is Stein, and such that there is a well-defined version of the Fukaya category for it. And so this categorical information is so that the most obvious way in which it enters Yang Li's work is through exact triangles of Lagrangians. So one has in his situation a triple of compact Lagrangians inside X, which satisfies some extra conditions. They are exact, they are almost calibrated, but these are not the most important restrictions. The assumption is that they fit into an exact sequence, but really we should say an exact triangle inside this category whose objects are Lagrangian branes. And that's what I'm indicating with this triangle here. Then, okay, so up to now they are simply Lagrangians, so they, supposing they define objects in this category, but we want to somehow then impose that the middle term, the thing which is at the center of this extension, is actually a special Lagrangian, and then deduce something from this categorical assumption that it's essentially the extension of two things inside this category. So what Lee proves is that if X satisfies some strong conditions that I think he calls automatic transversality and positivity, so there are somehow some strong infinite dimensional genericity conditions. Then if the extension is a special Lagrangian, you must have this following inequality of periods. So if you integrate the holomorphic volume form over over the cycles represented by these compact Lagrangians and take the arguments, they must satisfy this sort of phase inequality. And so this is actually a theorem which is proved in his book, that if you assume all these things, then special Lagrangian implies this kind of phase inequality, which is in fact what people usually mean by a stability condition in this categorical sense. So a triangle, exact triangle, implies some kind of phase inequality like this. And then well, you might ask, do we actually know somehow examples when these conditions are clearly satisfied? And maybe it's not completely clear from his book, but presumably they exist. And also, of course, you would like to prove the converse. So if we think of the analogy with vector bundles, this would be the easy some implications. The stability that somehow the solvability of a partial differential equation implies stability. So it's usually the easier direction, and then the hard analysis usually goes into proving the converse, that if you do have this kind of phase inequalities or stability, then you get solvability for the partial differential equation. And Lee sketches somehow a strategy to do this, which does not use the mean curvature flow. So it's a variation. So it's closer to the direct method in the calculus of variations. And it uses this setup, which was invented by Solomon for studying this variational approach. Is really based on the functionals that were introduced by Solomon. But it makes a lot of progress, but it's still very much an open story, even in this fine exact case. Then let me give you maybe some flavor for Joyce's proposals. So these are more. So these are the ones that really involve stability in a more algebra geometric sense. And Joyce formulates them in the compact Calabi-Yau case, but you can imagine that something similar holds in the Stein situation, for example, or more generally. So well, let's suppose we are in the same situation, that we have something Calabi-Yau with a well-defined Fukaya type category. And so is one of the conjecture he formulates in his book is that it actually should be possible to construct stability conditions in the categorical sense, which is called Bridgeland stability conditions. And we will see some of these ingredients later on in more detail, which take place on the Fukaya category. So they give you a notion of stability for objects in the Fukaya category, and which satisfy these best possible properties that, well, first of all, one of the ingredients in the stability condition is the central charge, which is somehow what allows to write these phase inequalities. So in Lee's work, the role of the central charge is played by these argument of periods, phases of periods. And here, Joyce, for Joyce, it's the same. So this numerical part of the stability condition that only sees somehow the topological data should once again be given by periods of the holomorphic volume form. So if you want to know what is the phase of an object, you simply integrate the holomorphic volume form over that object. That's the numerical part. And then coming to the categorical part, what should happen is that if you have a special Lagrangian, so some class inside this Fukaya category, which is represented by a special Lagrangian, then this object should be inside the category of semi-stable objects of some phase phi. So solutions of the special Lagrangian PDE should define objects which lie in this slice of the category, which is called semi-stable objects of phase phi. So this is the easy direction, the one that Yang Li sort of proves modulo this transversality in his work. And the hard part would be the converse, that if you have some isomorphism class of objects which is in this slice of semi-stables of phase phi, then the class inside the Fukaya category is representable by a special Lagrangian. So it's the hard direction in which semi-stability implies that you can solve the PDE. So that's the sort of precise statements that he makes. There are a lot of caveats because so somehow one needs to be very careful, and Joyce is very careful in. So he explains that in particular for this hard part of the conjecture, that semi-stability in this sense implies solvability of the special Lagrangian equation. So you need to allow weak solutions to be able to work in general, and this means in particular that you would need to allow inside your Fukaya category objects which are possibly very singular. So they should be Lagrangians that certainly are in general not embedded, they are immersed, but moreover, they should also possibly be very singular. So Joyce points out that really this point 3 is not completely rigorously formulated. So one will need to work out what is the precise extension that one needs to do first. And actually, Yang Li does some progress in this direction of understanding what kind of weak solutions we will need to allow. And so this idea will make a brief appearance also today, but it's the examples we will consider are so simple that so mostly we can work with smooth objects. So that's because we are going to impose a very strong symmetry and very strong assumptions. Okay, so the expectation is that these conjectures are extremely hard in general. So there's so one could ask if there's some kind of toy model or some class of some naive examples where one can actually prove something. So the examples which are sufficiently simple to actually be able to look at this special Lagrangian condition explicitly, but somehow which somehow are not trivial, so that they still encode some of the geometry of these phase inequalities and connection to stability in the Fukaya category. And there is a natural candidate for this class, which is a toric mirror symmetry essentially. So it's the case when you start from something which is compact, actually projective, a toric. We're going to call it X in the following. So from now on, X is going to be projective and toric. And so in particular, something symplectic toric. And there is a version of mirror symmetry in this setup, which has been studied a lot over the last 20 years, maybe more. And so the starting point here is a work of Leon Yao-Zaslow that we will briefly recall. And there's a paper from a few years ago by Tristan Collins and Yao that someone proposed to try and prove some version of these Thomas-Yau statements in this toric mirror symmetry setup. So for the mirrors of such projective toric manifolds. Now I'll So that in a few minutes, we'll see more or less what they proposed and what the obstructions were in that, so they found in their work. But for now, so let's just very quickly review this story. You have something projective toric, and so there are almost Calabi-Yau manifolds, which are a mirror to this projective toric X. The mirror is actually a whole family, and roughly speaking, it's parameterized by the Keller class, so by the cohomology class of the symplectic form on the mirror. And the geometry is quite simple, as we will see. These such mirrors to projective toric things are open bounded domains inside some algebraic torus, C star n. There's an additional crucial datum, which is a holomorphic function on the fibers of this mirror family. We're going to call it W. It depends on a Keller class, on the class of the symplectic form, which defines a point on the base of this mirror family, at least if it's sufficiently large. But this will always be the case for us. And so the construction of the actual mirror to such X is obtained by this Leon-Yau-Zaslow construction, which is very well known. So it's since we are in the toric situation, we get a special Lagrangian torus fibration over the momentum polytope, and so dualizing this special Lagrangian torus fibration, we get a mirror geometry which we're going to call U. It's this mirror. This dual torus fibration. It sits inside one of these fibers of the mirror family, so inside this affine torus. And Leon-Yau-Zaslow equipped this open domain with natural Keller form and holomorphic volume form. Plus, remember this, we have this crucial datum of the holomorphic function W, which really comes from the fact that U is Calabi-Yau, at least it's almost Calabi-Yau, but the mirror is not. It's a compact toric, so it's never Calabi-Yau. And this some sort of failure is remembered by this holomorphic function W on the mirror. So, the one crucial point on this story for us is this SYZ transform that relates Lagrangian sections inside this mirror almost Calabi-Yau. So Lagrangian sections inside U, they are sections for this mirror torus, for this dual torus fibration. And holomorphic line bundles on X, on the compact toric thing, once you equip them with the Hermitian metric. So if you might think that, so if the way we're going to think about is that we fix a holomorphic line bundle on the compact toric guy on X. And then if you have this extra choice of a metric along the fibers of L, and this as this varies, you get sections of the mirror torus fibration, so Lagrangians inside so there are sections which are Lagrangian. So the fact that they are Lagrangian is equivalent to the fact that L is holomorphic, and the extra choice of metric H on the fiber of L is deforming this mirror Lagrangian section within its Hamiltonian isotopic class. It's a simple computation that shows that if you vary H, you get different sections, but they are all isotopic through Hamiltonian diffeomorphisms. So this is the setup that we were going to work with, which is a natural thing to do, also following this proposal by Collins and Yau. So you would like to prove some kind of Thomas-Yau type results for such Lagrangian sections. So it's,
yeah. May I ask you a question? So when you talk about Hamiltonian isotopy, so what are the boundary conditions? Or I'm missing?
Yeah, the boundary conditions are, they are somehow hidden in the fact that L, the holomorphic line bundle, extends on all of X. So it's the holomorphic line bundle is defined on the whole compact, on the whole projective toric manifold X. And so this imposes some precise boundary conditions on what these Lagrangian sections should be. So they should behave at infinity so that the corresponding holomorphic line bundle extends on the whole of X. And I think people have worked out what the boundary conditions are, so, in the local coordinates, for example. Probably this class of Lagrangian sections is called admissible sections in some papers. It's a bit similar to the Guillemin boundary conditions, right? For Kähler metrics on if you write Kähler metric in symplectic coordinates on the momentum polytope, then you have these Guillemin boundary conditions that guarantee that the metric extends to the whole toric manifold X. So it's similar to these boundary conditions.
So geometrically, it's hard to say what is it, yeah? I mean, on the level of Lagrangians.
Yeah. I don't have a very good answer to that. I guess it's a very good point. Yeah. That's true. Thanks for the question. So, okay, so why were Collins and Yau so optimistic about this setup? So the reason is that if we can then work on rather than working on this almost Calabi-Yau U, we can, as you will see, we can translate things to X, to the projective toric mirror, and there is a very good analytic theory for which we can use, which is due to a lot of authors. Jacob, Collins, Yau have a lot of papers about this analysis you can do on the mirror. And then also there's a foundational work by Sekahidi. And then there was really a breakthrough by Gao Chen that led to, as you will see, to a more or less complete solution under some strong assumptions for the mirror equation that you need to solve to have the special Lagrangian condition. We will come to that. So analytically, there's a reason to be optimistic, and then you would like to go back and translate these analytic results into results which have a Thomas-Yau flavor. So either these phase inequalities for periods, or maybe stability conditions on a version of the Fukaya category. And this was the obstruction in the Collins-Yau work. So they, actually 99% of the paper and then all these subsequent papers are about doing the necessary analysis on X. But so what was missing was how to translate back into results which have a Thomas-Yau flavor. Okay, so let me then tell you about one of these results. So we are in this toric situation, and moreover, we also impose further restriction on X. It's not only projective toric, but also Fano, or more generally, it can be weak Fano. So the anti-canonical bundle on X is either ample in the Fano case, or it needs to be big enough in the weak Fano case, if you want to generalize, have more examples in that way. Then, just as before, we fix a line bundle on X and work on Lagrangian sections of the mirror almost Calabi-Yau, which are obtained from metrics on L. We have this assumption that the dual line bundle, so the inverse line bundle, is positive, is ample. It's not really essential, but it simplifies a lot of the statements, and it's natural from a certain viewpoint. I will explain. Then the statement is that if, consider this class of Lagrangian sections, and you want to find conditions under which you can, so this class of sections contains a special Lagrangian. And the statement says that indeed this is a Thomas-Yau type condition. So that there are finally many triangles inside the relevant version of the Fukaya category in this case, which is called the Fukaya-Seidel category. So it involves both this mirror family, but at the same time, the datum of this Landau-Ginzburg potential. So there are these finally many triangles inside the category, and they are in bijection with toric subvarieties of X. but you can take that as an index if you like, just some index V enumerating these finally many exact triangles. And then the condition that we are able to find a special Lagrangian section among all these sections is a phase inequality between objects which appear in these finally many exact triangles. So each of these triangles gives a phase inequality between periods of a holomorphic volume form, which is a negative x of the Landau-Ginzburg potential times omega naught, which is the toric d log xi wedged several times volume form. And yeah, so each triangle gives a potential obstruction in the form of these phase inequalities for periods. And if all these inequalities hold, then there is a special Lagrangian section among all these SYZ sections. At least if you work in this range for the phase angle of Lagrangians, which is called supercritical, and which is this range which says that the Lagrangian angle, the Lagrangian phase angle, should be sufficiently large with respect to the dimension. So you have this constraint on the phase angle of your Lagrangian, which is more and more restrictive when you increase the dimension of your manifold. For example, in dimension n equals 2, it essentially gives no condition at all, and we don't need to work in this supercritical range. But if you go up with dimension, it becomes more and more restrictive. And the reason is that somehow this analytic theory that I was referring to really works well with when the phase angle of the Lagrangian is sufficiently large with respect to dimension. So if this is called supercritical range by analysts, and so it's known that if you move away from this supercritical range for the Lagrangian, the special Lagrangian equation, then strange things might happen. And maybe in general, analysts know that you don't expect smooth solutions, and you will generically you will only have very, very weak solutions. But if you insist on the supercritical range for the phase angle, then it's true that you can reformulate the analysis in this way, using exact triangles and phase inequalities. And then you get a smooth classical solution. So I would like to maybe explain a bit more about the strategy of the proof. So there's some expanding on some of the things I already mentioned. So firstly, you have the starting point that you can reformulate the special Lagrangian condition on this almost Calabi-Yau on X. So this is maybe not surprising since there is such a strong link between the Lagrangian section and the line bundle with the emission metric. So the special Lagrangian condition becomes a condition on the metric on the fibers of the line bundle. And it's an equation that is called the formed Hermitian-Young-Mills. It's written down here. So superficially, it looks a little bit like a complex Monge-Ampere equation. And actually, it is the same as a complex Monge-Ampere in dimension 2, but only in dimension 2. So starting from dimension 3 onwards, it's no longer complex Monge-Ampere, so you cannot use classical Calabi-Yau type results to solve it. It's more difficult, and it's open in general, except for this supercritical range. But apart from that, you can see that somehow the analogy between the two equations is clear, and some of this SYZ transform between metrics and Lagrangian sections is precisely what matches these two partial differential equations. So this is first ingredient. Then we explain a bit better what is this supercritical phase. So you can reformulate this. So now you work on the mirror X, and you work with the Hermitian metrics rather than Lagrangian sections. And then you can rewrite the the formed Hermitian condition in a way which is actually closer to the special Lagrangian equation. So you rewrite in terms of the relative eigenvalues of the curvature of the Hermitian metric with respect to the background Kähler form on X, and we fixed. And then it becomes a trigonometric PDE of this sort. And this is the correct formulation to do analysis with it. And this is what analysts know. So you need to reformulate it in this way, and then it actually becomes possible to apply a whole range of tools that they have, from starting just with the maximum principle, but the more complicated versions of it that allow to have a good theory, at least in the supercritical range. So when the phase angle of the corresponding Lagrangian is large compared to dimension. And so this is the bound on this phase angle that we mentioned before. And then this is the analytic existence theory. If you want to solve this deformed Hermitian-Yang-Mills condition, then if the phase angle is sufficiently large, this deformed Hermitian-Yang-Mills condition is implied by this trigonometric partial differential equation, and that has somehow better analytic properties, which in the end allow you to find a criterion to solve the equation. And this is numerical, so it's finite dimensional. This trigonometric equation in the supercritical phase is solvable smoothly if and only if you have these finitely many inequalities, these positivity conditions for these finitely many integrals, which are in bijection with subvarieties of with irreducible subvarieties of X in general. This is not necessarily in the toric case. In the toric case, it's enough to check it for finitely many irreducible toric subvarieties. So for components of, you can just check it for components of the toric boundary. So it becomes a finite problem. You have to perform these finitely many checks for these integrals. If they are all positive, then there is a unique smooth solution of the trigonometric equation, and so of the deformed Hermitian-Yang-Mills, and so of the special Lagrangian equation for the section you get from the metric. So now clearly the problem becomes some reformulating this criterion in terms of exact triangles in the Fukaya category, rather Fukaya-Seidel category in this case. So the first observation is that we can start working on X rather than on the mirror, and try to see if this some of these positivity conditions, which people call Nakai-Moishetson criterion for the partial differential equation, if they are equivalent to phase inequalities for some algebra geometric quantities on X. And that's the case. So we are able to construct objects inside the boundary derived category of X, of our toric weak Fano manifold, such that at least if we only look at the semi-positivity condition and worry about the strict inequalities later, then this Nakai-Moishetson criterion weakly is the same as phase inequalities for this sort of algebra geometric quantities attached to these objects in the boundary derived category. And this sort of quantities, these integrals of X times the chain character, are called central charges in certain algebra geometric literature. So phase inequalities of central charges, at least if we don't worry about the strict inequality yet, are the same as this Nakai-Moishetson criterion. Then we do worry about strict inequality, and so we can remove the problem, at least if we are in the toric case, by assuming that the Kähler class is sufficiently generic. So the problem comes from Kähler classes such that the equality sign is actually achieved in one of these integrals. But this is a a closed condition. So we can assume that the class of the symplectic form is sufficiently generic so that this pathology does not occur. And then the strict inequalities are actually equivalent. So the Nakai-Moishedson criterion that analysts found is actually the same as these phase inequalities for central charges on DBX, on the bounded derived category for this set of objects. Now, this genericity should be a bit artificial. So you probably so that the idea from Joyce's monograph is that it's not really necessary. You can do without this genericity condition, but you should then allow weak solutions somehow. So the problem would be extending this analytic theory to understand what happens if this Nakai-Moishedson criterion holds only weakly, and you would expect that you still get a solution, but maybe a weak solution in a suitable sense. Then one further step is to translate this proposition to the Fukaya-Seidel category, and this becomes so the first step to do it is to use these major results about mirror symmetry in this case. So the equivalence you have between the bounded derived category of your of a projective toric manifold X and this Fukaya-Seidel category of the mirror. So that's really a major ingredient, and it allows to translate so these objects, this collection of objects in DBX into a collection of objects in the Fukaya-Seidel category. Okay, and then the problem is then we do have the collection of sort of Lagrangians. Well, at least one of them is the Lagrangian section, and the others are presumably represented by some kind of Lagrangians. They might be generalized Lagrangians in, they are really objects inside this Fukaya-Seidel category. You might wonder how geometric they are. Then the missing ingredient is really translating this phase inequality of algebra geometric central charges to something that involves periods. So as expected in both from both Young Lee's and Joyce's works. And the ingredient to do that is a theorem by Iritani, which people call the gamma theorem, which does precisely that in this toric weak Fano situation. So this is really the point in which the weak, well, all three assumptions, sorry, all two assumptions really are. Well, the toric assumption is of course necessary for the whole setup, but the weak Fano assumption was not needed so far. We could have worked with something which is toric and projective, but not necessarily weak Fano. But as far as I know, this gamma theorem really requires this Fano assumption. And it's so a wonderful result that allows to relate this sort of algebra geometric central charges for holomorphic vector bundles to periods of the holomorphic volume form on the mirror geometry. Now, however, if you look at the correspondence, so it's not so straightforward as in our integrals, right? So our integrals are something like negative exp times the Chern character, and these integrals that go into Iritani's gamma theorem are much more complicated. So the main extra ingredients are really so a function with values in cohomology, which is called the given times I function, this gadget here, plus something which is then a constant cohomology class, and it's called the gamma class of your weak Fano. So somehow these give obstructions to a direct comparison between central charges and periods. And the conclusion of this sketch of a proof is that then we need to carefully compare the two things and show that in this limit that we're looking at, so it's a limit when limit that which appeared in our statement. So it's a limit when you rescale the symplectic form, make it very large with the parameter k, but also at the same time rescale the Lagrangian section in the sense that it's mirrored to a high tensor power of the line bundle. Then in that limit, the comparison is possible, and the phase inequality of central charges is equivalent to the phase inequalities of periods. So the limit when you rescale the Kähler form is classical. It's called the large volume limit. What is somehow slightly non-trivial in this case is that at the same time we also rescale the Lagrangian section, so we make it sound very, very large at the same scale as the large radius limit, as the large volume limit. And this is done by saying that it's mirrored to kth tensor power of the line bundle. So this is sort of a large volume, large Lagrangian limit. And actually, it already appeared in this proposal by Collins and Yau from a completely different perspective. But it's the same sort of limit that they had. So it's the right sort of limits to be able to compare central charges and periods and apply all our previous results to get this sort of Thomas-Yau results. Exact triangles fix the solvability of the special Lagrangian equation for these very simple Lagrangian sections. Okay, so in the last maybe a few minutes, so this was what I explained was more similar to Yang Li, perhaps because in the end it only had to do with exact triangles and inequalities of phases of periods. And now we turn to more to Joyce's viewpoints, which is more requires more algebraic structure. It requires one of these Bridgeland stability conditions. And so let's start maybe with the case of surfaces. So now X, we specialize to the case when X is a toric projective weak del pezzo surface. And so there is a very well-developed theory of stability conditions in this case on the category of on the boundary derived category of coherent shifts on X. So remember very roughly we've seen that one of these stability condition means that we should have some kind of topological numerical quantity, which is called the central charge, which we can evaluate on one of the objects, for example, on a holomorphic vector bundle. And it's once again one of these integrals that we have already seen. And so that's natural. And the highly non-trivial part somehow is the categorical part of this notion, which is entirely encoded in what people call the heart of a bounded structure on the bounded derived category. So you can think that somehow so that there is the standard choice would be that A is just the category of coherent sheaves on X. However, the whole point of this theory is that that choice will not work. It will not give a good notion of stability. So it will not lead to a good framework in which you can actually compare the phases of such topological integrals. And you need to allow more general T structures on your category. So some different ways in which you can, very roughly speaking, different ways in which the bounded derived category is the derived category of some abelian category. It's not exactly like that, but it's roughly like that. So something that is this category A is somehow a generalization of the category of vector bundles. It's some more exotic version of vector bundles, and actually for our applications they will always be categories of complexes of well, two-term complexes of vector bundles, or maybe complexes of vector bundles in a slightly more complicated situation, but that's roughly the idea. So these things have been constructed by algebraic geometers on surfaces in dimension 2 with with a standard construction. And then in this case of dimension 2, you can actually prove direct relation to such algebrogeometric stability conditions. So you fix, so it's the same setup as before. We have a line bundle. We're still assuming that the inverse line bundle is positive, is ample. So in particular, you get that the slope or the Mumford-Takemoto slope of L is negative. And then the statement says that the solvability of the special Lagrangian equation inside the isomorphism class of a shifted Lagrangian section is governed by this stability condition. So if you get one of these standards, you can construct one of these standard stability conditions so that if you carry it over to the Fukaya-Seidel category through this mirror equivalence, then it gives a stability condition on the Fukaya-Seidel category. This shifted section is an object in the category. It lies inside this heart, so it's inside the abelian, the selected abelian part of the category that we are considering. And if this corresponding object is stable in this algebrogeometric sense, then the special Lagrangian equation is solvable. The central charge is roughly the correct one. So it's given by a period, as in Joyce's expectation. Not exactly that, but there's the correction terms are small in this large volume, large Lagrangian limit. So this is one direction. And the opposite direction, so proving that if the special Lagrangian equation is solvable, then you get stability, is also true modulo a conjecture which is so it's a well-known conjecture in this kind of algebraic geometry. It's due to Arcar and Miles, and it gives a characterization essentially of the maximal destabilizing objects of line bundles on surfaces. So it's still open. It's been proved in a few cases, in particular for toric cases, for toric Fano cases. It's known in the first two toric Fano situations. So when you blow up a point or you blow up 2 points, it's also known for P1 times P1 and P2, but these are trivial from the viewpoint of our theorem, so they don't really give new examples. But these two toric examples are fine. So so all results are known in these cases. And okay, so I think essentially time is up, so maybe I have one more minute, and perhaps I'd like to say that yeah, something like that also happens in dimension 3. So when you go to the toric weak Fano threefolds, you might want to prove a similar result, so a kind of a Joyce-like result for these Lagrangian sections. And you can do something similar. However, it's much more restrictive. So there is a similar theorem, but unlike the case of surfaces, the construction of stability conditions on threefolds is well known to be a very complicated matter. So it's only kind of the last few years that such things have been constructed by algebraic geometers. And in particular, if we rely on a construction which is due to Macri and his collaborators, then we can prove something under some much more restrictive assumptions. You have a very similar conclusion for shifted Lagrangian sections in these mirrors of Victor Pets of Fano threefolds. However, yeah, so I think if we insist on Fano rather than weak Fano, then the only example really we get from this theorem is for now the blow up of a complex projective tree space along a line. So it would be essential to relax these conditions and try to find more examples. In particular, this will not apply to the blow up of P3 in one point. One needs to do something else there, although I think probably some similar results can also be proved in that case. Okay, I think I should really stop here, and thank you for listening.
Thank you very much for this very interesting talk. So, in case there are any questions, please go ahead. So I don't see any people online who are asking. I have a couple of questions myself. So some are related to your earlier statements.
Yes.
So in one of them, you were saying that Lagrangian branes that appear in this theory have to be very singular Lagrangians. So they have to be immersed, but more singular than that, you said at some moment. So
yes.
What does this mean? They are in what sense they are more singular than immersed?
Okay, so yeah, I think so. The question is we have this. I don't know if you can see a little bit this blackboard maybe.
Yeah, yeah.
Okay, so we have these objects. We construct SV, which is inside this BBX. And so these are, in general, they are complexes of vector bundles.
Yeah.
So it's a sort of inductive construction on these things are in bijection with the toric subvarieties inside the mirror X. And we do an induction on the dimension. So we only know that they are represented by some isomorphism class of complexes. Then we have this equivalence from BBX into this Fukaya-Seidel category. Why? And so we send one of these objects SV to some objects to some object LV. So if we just do that, we don't know very much about these objects. So
but LV is an iterated triangle, maybe
right,
iterated cone.
Yes, that's true.
Of embedded objects, right? Because is this true of embedded or of immersed objects?
It's yeah. So this is a. No, I think they. Yeah, I think probably they are iterated extensions of embedded objects. Yeah.
Of embedded objects, even.
Yeah. I think probably it might even be the case that they are iterated extensions of sections of Lagrangian sections. Yeah.
So then, in fact, I think there are ways to view them really as immersed Lagrangians. I don't think you need them to be so singular as that. It depends in exactly what context maybe you work, but
yes, yeah. So that's true. So this is so I asked a few symplectic geometry or some people who know about this in more detail. And yeah, so one of the basic questions is, for example, you have on the basic case maybe on this side is that you have a short exact sequence like some tensor power of a line bundle, then it's twisted by some divisor D, and then you go to this K tensor O C MD. So the one of these objects is this cone. So it's in other words, is this the mirror of this torsion coherent sheaf here.
Mm-hmm. I understand.
Right. So I asked some experts what is so what in this Zaslow type of toric mirror symmetry. What is the mirror of one of these torsion sheaves, which are somehow supported along the toric boundary? But it's in general a thickened component of the boundary.
In any case, I understand the issue. Yeah, okay.
I think the issue is probably the thickening. If you one of these people told me that if we want to allow thickenings in higher dimension, then we somehow there is a way to think of them as immersed rather than embedded Lagrangians. But yeah.
All right. In any case, thank you very much. I was just curious about what.
Thank you. So yeah, this is one of the questions I also have for sure. So it's.
So I had one other question that was much less maybe complicated. I just didn't understand one of these statements. There was a statement with many authors. I think.
Yes.
Let me see. Yeah, this one, the Jacob.
Right.
Just a second.
Yes.
Yeah, so here I didn't understand something that was very basic. So I didn't understand actually the part after then. Then there exists a smooth solution of the constant Lagrangian phase equation. And I didn't understand for any or some representative. So what does it mean?
Yes.
Because you have an if and only if after that. So this is what I didn't get. I didn't get, what do you mean for any or some? Is it for some or is it for any? Because it's
just it's just probably it's a grammatically awkward way to say that solvability does not depend on the choice of representative.
Okay.
Yeah, and that's yes. So that's also I think it's probably also evident from this criterion, right? Because this is a cohomological, and so it will not depend on the choice of a representative for the background scalar form. Yeah.
All right.
So, but a priori, it's if you just look at the equation, so you just look at this equation, it's formulated for the relative eigenvalues of the curvature with respect to background metric. And it's not clear at all that it will not depend on the choice of background metric. Yes, and maybe it's even false away from this supercritical phase. It's not known somehow. I think even that is not known away from supercritical, I guess. Yeah.
All right. Thank you very much.